Welcome to the video for task 16. And again, we're going to jump right in where we left off on the previous video. So we're still on the incremental net monetary benefit sheet. And we can see that there's been a couple more columns that have appeared. In these columns, we're going to calculate the probability that treatment A and treatment B is cost effective. And we're also going to calculate where the cost effectiveness acceptability frontier would be plotted given the current settings in the model, in particular the current cost effectiveness threshold. Okay, so we're going to begin with the cost effective, this column with cost effectiveness for treatment A. We need to determine whether treatment A is cost effective on each iteration. So we're going to do this for each iteration, and then we can just average over those iterations later to get the probability that it's cost effective across all of those iterations. So for now, we just need to have a 1 or a 0 in this cell. A 1 if treatment A is cost effective for this iteration, and a 0 if treatment A is not cost effective on this iteration. And as we talked about earlier, this cell here tells us whether treatment A is cost effective. If this is positive, that means that treatment B has a positive incremental net monetary benefit versus A, and so treatment B is cost effective, treatment A is not. So if this cell is positive, we want a 0 here, treatment A is not cost effective. And if this is negative, as it happens to be in this case, well then treatment A is cost effective. Okay, so we can just do a very simple if statement. If this cell here is negative or equal to 0, we could say. So if it is less than or equal to 0, then give us a 1 here, otherwise give us a 0. And by the way, the probability that this is exactly 0 is infinitesimally small, but it's good practice not to create an error in the model if it actually is 0. So if BM38 is less than or equal to 0, that means treatment B does not provide any incremental net monetary benefit, so treatment B is not cost effective. Treatment A is, we get a 1 in this cell. Otherwise, well, this cell must be positive, which means treatment B is cost effective, so we want a 0 in this cell. And then this is going to be copied down. We don't need to lock anything, so let's just press enter. And that's going to get copied down to the remainder of those 10 iterations. Okay, and then in step 16.2, we need to do the same thing for treatment B. And there's a couple of ways we could do this. We could have a very similar formula where we would just flip the direction of the inequality and put that formula in for treatment B. Or we could just recognize that if this is a 1, if treatment A is cost effective, well then by definition treatment B is not, and so that's 0. And if this is a 0, well then this needs to be a 1. So a couple of different ways which are both logical, they'll both work. We'll do the simple one here. So we're going to say, if this is 1, I want a 0. And if this is 0, I want a 1. Another way of doing that would just be to say 1 minus this. You don't even need an if statement. So we're just going to do that. By doing 1 minus, if this is 0, this is 1. And if this is 1, this is 0. This, of course, works when we just have these 2 treatments. A little bit more complicated if you have a model with 3 or more different treatments. Okay, now we're on to step 16.3. Calculate the probability that treatment A is cost effective. So the probability is simply the average of all of these. So we can probably just borrow it from here. Let's just copy that. There we go, 99.6%. So if you recall, there were a few of those iterations where there was a positive VPI, where treatment B was cost effective. There were just a handful of them. And you can see out of 1,000, well, not very many. 99.6% have A being cost effective, just 0.4% would have B being cost effective. We're now moving on to the same thing for treatment B in this cell. So we can just do a similar thing, can't we? This 1 minus, if we just do 1 minus, that's going to give us the probability for treatment B. Again, it works when we just have 2 treatments. If you had many treatments, well then you'd have to use a similar formula to this. for each of those treatments. Okay, and then this brings us to step 16.5, which is to locate the cost-effectiveness acceptability frontier given these settings in the model. And the cost-effectiveness acceptability frontier is distinct from the cost-effectiveness acceptability curve. The cost-effectiveness acceptability curves are just plotting these numbers here. So we would plot a curve that shows 99.6% for A and 0.4% for B. And then as we change the cost-effectiveness threshold, these figures would usually change as well, and we'll get this nice curve. The cost-effectiveness acceptability frontier plots the cost-effectiveness acceptability curve, but only for that strategy that is cost-effective, right? And it is possible for a strategy to be considered cost-effective insofar as BM33 is positive in the case of treatment B, right? Treatment B will be cost effective. It is possible for that to be the case and the probability that treatment B is cost effective to be lower than 50%, right? It's possible for the probability of treatment A to be cost effective to be higher than that for treatment B, and yet the expected incremental net monetary benefit for treatment B is positive. And that can happen when there's a skewness, where there are fewer iterations where treatment B is cost effective, but on those iterations, the incremental net monetary benefit is much greater than the loss on those other iterations, right? And this can happen. Okay, so what do we need to do? We need to pull in either this value or this value, depending on which treatment is cost effective. So we can do an if statement again. So if, and what are we testing? Whether this is, let's do less than or equal to 0. Less than or equal to 0. So if it's less than or equal to 0, that means treatment A is cost effective. And if treatment A is cost effective, well then we want this value in cell BS33. And if not, then we want this value. Okay. So right now, because treatment A is cost effective, we're pulling in this value here, 99.6%. As we change the cost effectiveness threshold, eventually treatment B will be cost effective and we'll be pulling in this one instead into our CF. Okay, and that brings us to the end of task 16, and I'll see you in the next video for task 17.